All right, so now we're going to finish the second section of 4.4. So we're still in second 4.4, but we broke it up into 2 different days. So we're finishing this now. We're going to focus on conditional probability. Something that we've already talked about, already done in the last section. Because we know if we're trying to find a probability of 2 events happening, A and B, that we can go ahead and solve this by finding the probability of A times the probability of B given A. So the second event happening given that the first one occurred. So if we want to solve for the conditional probability, which conditional probability is finding the probability of an event happening after another event already occurred. So in this case, it's finding the probability of event B taking place after event A already occurred. And if we want to find a formula for solving for this, we just need to isolate it. So to isolate it, we would divide each side by the probability of A, and that will isolate our probability of B given A. And this is the formula that you will get. All right, you will get this formula when you're giving your test, but you will need to know how to apply it. All right, so let's go ahead and use it, the formula of the probability of B given A equals to the probability of A and B divided by the probability of A. Let's go ahead and use this. So remember, this slash does not mean division, but it means that this event B is happening after event A already took place. So it's the probability of B given that event A took place. All right, so if we read through this, a box contains black chips and white chips. A person selects 2 chips without replacement. If the probability of selecting a black chip and a white chip is 15 out of 56, and the probability of selecting a black chip on the first draw is 3 out of 8, find a probability of selecting the white chip on the second draw, given that the first chip selected was black. So what I would suggest you do for this is instead of using B and A, we're going to create our variables. And the variables are the 2 events or what we want to take place. So in this case, we want a white chip. And then we want a black chip. So I'm going to go ahead and rewrite this as W and B. I'm going to rewrite my formula. So it tells us that we want a white chip on our second draw. So that means that we're looking for a white chip given that a black chip was first. So now we would set it equal to the probability of P of A and B. So that would then be the probability of B and W based on the letters that we're using now, over top of the probability of A, which is our second part of this given, but it's actually our first event that took place, but it's the second thing written. So it'll be over top of the probability of B. So then that means that we're looking for this. Well, the probability of the black and white chip happening is 15 out of 56. So it's 15 out of 56. And the probability of a black chip being drawn first is 3 out of 8. So now we can rewrite this as 15 over 56 divided by 3 over 8, which is the same or equal to 15 over 56 times 8 over 3. 3 goes into 15 5 times, 8 goes into 56 7. So the odds of you selecting a white chip, given that you selected a black chip first, is 5 out of 7. All right, so for this one, we now are doing a survey on women in the military. A recent survey asked 100 people, right? In the last section when we're going over this, a lot of you guys would stop or forget how many total people we were doing in the surveys, and you would oftentimes put it over top of just our female total or male total, not over the total number of people. So remember, there's 100 people. If they thought women in the armed forces should be permitted to participate in combat, and the results are shown below. And they want us to find these probabilities that the respondent answered yes, given that they were a female. So we're going to go ahead and use the formula. I'm going to write it over here first. So the probability, actually I'll just write it underneath of it. I was just trying to save space, but it's a probability of B given A is equal to the probability of A and B over top of the probability of A. So now we're going to rewrite these letters. Instead of A and B, we're going to come up with our own. So since they want us to go find who says yes, given that they're female, I'm going to use Y for yes and F for female. And they want the female, it's the answer, the respondent answered yes, given that they were a female. So that means that the female is the first event that takes place. So the way that we would write this is a probability of yes, given that they're female. So that means it's equal to the probability of a female and they said yes, divided by the probability that they are a female. So let's go ahead and use this to use our chart to fill this in. So first we're looking for probability that they are female and they said yes. Well, here's all the people who said yes. And here's the people who were female. So that means there are a total of, you can't really see it right now, I kind of has darkened it out too much, but right here, there's a number 8. So there's a total of 8 people who said yes and were female. And there's a total of 100 that they surveyed. So that means 8 out of 100 were female and said yes. And then it's the probability that they were female. Well, there's 50 females that they surveyed, so it's 50 over 100. So this is equal to 8 over 100 divided by 50 over 100, which is then equal to 8 over 100 times 100 over 50. This then cancels out. 8 is divisible by 2, so that will be 4. And 50 is divisible by 2, which is 25. So that means we have a 4 out of 25 chance of picking someone that said yes, given that they were a female. All right, now the last part of this section is finding the probability for at least. So before, when we did this last section, so if I said find a probability of getting at least 1 heads when flipping a coin 3 times, I made you guys go through and figure out all of our sample space, heads, 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 tails, and so on. I'm not going to fill it all in because we did this already. And then we counted them. Well, what happens if instead of 3 times, I said you're flipping the coin 6 times? This will then become really, really hard to go through all the sample space because we have a lot. So the way that you do this is you think about this. If we say at least 1 heads, that means the only time that we do not have at least 1 heads is if we were to flip it tails every single time. Besides that, we would have 1, 2, 3, 4, 5, or 6 heads. So what we do in this probability is we find the probability that it doesn't happen, so all tails, and then we take its complement, which will be 1 minus the probability of our event. All right, so let's go ahead and use this to solve some questions. All right, so it says a coin is tossed 5 times, find the probability of getting at least 1 tail. So before, like I said just a second ago, I would have had you fill out your entire sample space, which is just way too much. So if they're getting at least 1 tails, that means the only time that this doesn't happen is when we flip all heads. So it's easier for me to find a probability of getting all heads. Well, we're flipping a coin 5 times. So remember I told you in class, if you're unsure of how to find a probability at times, you can just write these dashes and they can represent our event 1, so flipping our coin the first time, our event 2, our second flip, our event 3, our third flip, our event 4, our fourth flip, and our event 5, our 5th flip. So then we're going to go through and say, all right, well, what is the probability of getting a heads on our first toss? That'll be 1/2. What's the probability of getting a heads on our second toss? 1/2. Heads on our third toss, 1/2. Heads on our fourth toss, 1/2. And the 5th toss is 1/2. And whenever we have these different events, and we want to find the probability of all of them happening, we are going to multiply them. So this is the same as 1/2 raised to the 5th power, which is 1 over 32. So that means the odds of flipping all heads is 1 out of 32. So if we want to find the odds of getting at least 1 tails, we need to take this complement. So 1 minus 1 over 32, which is then equal to, we would have to multiply this by 32 over 32 to get common denominators. So it'll be 32 over 32 minus 1 over 32. So it's equal to 31 out of 32. So that means if we're flipping a coin 5 times, we have the probability of 31 out of 32 of flipping at least 1 tails. All right, now this is the last one we're going to go through. A game is played by drawing 4 cards from an ordinary deck and replacing each card after it's drawn. Find the probability that there's at least 1 ace. So that means if there's at least 1 ace, the way for us to solve this, rather than going through all the different possible hands that we could get, is we'll look at these 4 events, these 4 cards that are being drawn, and they're being replaced, replacing each card, so that's key. Right? In our first one, rather than going through all the different possibilities, we're going to look for when we can have how many different hands we can have with no ace. Because if we want to go through and figure out, well, can we have an ace here, an ace here, an ace here, there's so many different possibilities that we can have that we're going to figure out, well, no ace. Well, there are 48 cards in the deck that are not aces. Let me write this in a different color. So we have 48 cards in the deck that are not aces. So that means in our first card drawn, it would be 48 out of 52. There are 48 cards in our second card, because we're replacing it, that are not aces out of 52. And again, 48 out of 52 and 48 out of 52. So we can then take this 48 out of 52 and we can raise it to the 4th power because we'd be multiplying it by itself 4 times. So then this is equal to, we can reduce and say, well, it's 12 over 13 raised to the 4th power because 48 over 52 can reduce to 12 over 13. All right, then from here, you can do 12 divided by 13, and then you could raise it to the 4th power. And this is equal to 0.726. So then if I want to find a probability of getting at least one ace, because this is no aces, I need to take its complement, 1 minus 0.726. And this will give us 0.274. So we have roughly a 27.4% chance of getting at least one ace if we draw 4 cards and replace each card. All right, that is it for this video.